Hey everyone, wherever place you are watching from, this is a YouTube tutorial brought to you by the academic unit of CCC SP Futa, and today we'll be looking at this course, Chemistry 102, which is mainly composed of organic chemistry. That's everything the course entails, but we'll be breaking it down. I'll be taking the first part, which is introduction into it. So now, what is organic chemistry? Organic chemistry is divided into several branches. We have the inorganic chemistry, we have organic chemistry, we have nuclear chemistry. In inorganic chemistry, we deal with acid, base, thick compounds you can produce in the laboratory. While in nuclear chemistry, start talking about radioactivity, nuclear fission, nuclear fusion, and co. So in organic chemistry, the way it is defined in the easy form sense is that it is the chemistry of carbon compounds. The chemistry of carbon compounds, especially hydrocarbons and derivatives. So it is chemistry of organic compounds or chemistry of carbon compounds. The reason why it is chemistry of carbon compounds is because majority of the organic compounds you would see have carbon as the main element in it, and many times they are usually having hydrogen with them, or they should have the derivative of hydrogen. Derivative of hydrogen means you are replacing the hydrogen in them with probably oxygen or nitrogen, phosphorus, sulfur, and non-metals like that. So when you have compounds like this, that's carbon as the centered, element in it, and hydrogen with it, or the derivatives of hydrogen or derivatives of hydrocarbon, rather, we call that organic compound. Although it is not every compound that has carbon in it is an organic compound, but majority of it. So it's still safe to say that organic compound is the chemistry of carbon compound. Some inorganic compounds have carbon in it. You have the likes of carbon dioxide. This can be produced in the laboratory. So that is why it is an inorganic compound. Because organic is coming from organisms. Inorganic is not from organisms. You understand? So you have CO2, H2CO3. All these are inorganic compounds, although they have carbon in them. So organic chemistry is just chemistry of carbon compounds, especially hydrocarbons and derivatives. Now let's take a little bit of history about this organic chemistry. In a lot of years back, the likes of 1801, 17s, and co. Scientists believe that organic compounds can only be gotten from organisms, that is living organisms, because there is a need of an huge force. They call it the vital force that you need before you can produce organic compounds. So that's their belief, that except organisms give out organic compounds, except organisms give out acids like CH3COH, except organisms give out CH4, except organisms can be human beings, can be plants, can be animals, and co. So except they give it out, because of the force they can give out to produce that, we cannot have organic compound. That was their belief until 1828, when Frederick Wohler, this man in 1828 did something. He got ammonium cyanide, that is NH4CON. Got ammonium cyanide, then he decomposed. Ammonium cyanide is an inorganic compound. Then he decomposed this through it, then he got NH2. This is urea. I hope you know urea is from living organism. Urea is found in our urine. Human beings produce urea, and living organisms, they produce urea. So you now notice that urea, which is an organic compound, can be gotten from an inorganic compound. So meaning you can prepare organic compounds in the laboratory. It is not only living organisms that can give out organic compounds now. Even from inorganic compounds, you can get organic compound. So that was when they did away with this vital force theory. The vital force theory was done away with in 1828. Now let's look at how we define organic chemistry. We said carbon is the main element that is centered amongst organic compounds. Why is carbon very unique? They say uniqueness of carbon. Why is it so unique? Let's look at the uniqueness of carbon. Why? The first one is that carbon is tetravalent. The meaning of tetravalent is that it has 4 valence electrons. Carbon is number 6. So if you have to group it in your key element, you have 2, 4, And you need how many for A to be complete? You need 4, right? So it has 4 elements. If you want to draw this in the shell now, this is carbon. Tetravalent, making it that it can combine with 4 other elements. You understand? So it can combine with 4 different other elements. It can combine with, it has 4 electrons willing, it's willing to share 4 different electrons with all other elements. So it is tetravalent. That was one of why it is unique. But it is not the only tetravalent element. So why is it still unique? Another thing it does is catenation. Carbon can catenate. Catenation means ability to form chains of atoms. You should be linking yourself. Let's assume this is you. The ability to link yourself together, the same you. You have like multiple of yourself. Then you should form chains, without breaking. So carbon can do that. So it can link its atom. Can form long chain of its atom. You can form long chain without breaking. That's why you see shapes like this. It's ready to continue going as many lines as it can form. Another thing that makes carbon unique, aside from it can form single, double, triple bonds. That is, it can form multiple bonds. So it can do a carbon to carbon single bond. It can do a carbon to carbon double bond. It can do a carbon to carbon triple bond. So it can form bonds of, it can form multiple bonds. Carbon. Another thing carbon is that it forms strong, bond. Strong covalent bond. Carbon can form strong covalent bond. It is, since it has to, share electrons, so it participates in covalent bonding. But the covalent bond it participates in is usually a strong one. So this makes carbon, these are just few of what makes it unique. Part of what makes it unique. With this, it is very unique and can give us as many elements or as many compounds as we want, making it very suitable for organic chemistry. Take the characteristics of organic compounds. So what are the characteristics? The first one is that they are covalently bonded. Organic compounds are covalently bonded. That is, it is covalent bonding that exists between the atoms. Carbon takes hydrogen, they share electrons. It takes another hydrogen or takes oxygen or takes nitrogen. So they share electrons. Electrons are jointly shared instead of ionic, where you have to transfer the electron you are not really using like that, or you outermost electron to another element, to another atom rather, or in coordinate covalent or in metallic bonding. So they are covalently bonded. All of them, every of the atoms you see in that compound, they share electrons. Another thing is that they are combustible. That is, they burn in oxygen. They are combustible. They burn in oxygen. So covalent organic compounds are combustible. They burn in oxygen. They have the likes of ethanol burning in oxygen. And when they all burn, they give carbon dioxide and water vapor with energy. That's why you see that most of them, they are used in fuel. These fuels we use at home to cook and a lot of things, because they give energy, they give heat. But let me give you a short formula, for CDT and CBE questions. Imagine you are asked, or you are told that hydrocarbon bonds combust in oxygen. What would it give? The first period to give CO2 and H2A. But there is a short formula. When I mean short, there is a short formula you can use to balance this equation up because of time plus energy. So what you just need, let's say, assume they say hexane or propane or propene. So why it is an hydrocarbon, C and H bonds in oxygen. The C and H hydrocarbon, the formula is just for hydrocarbons, not CHO or CH. You have to balance that manually yourself. But for CH, once they give you your C, the number of atoms, call it X, H, call it Y. So your oxygen, the number of oxygen needed to for this combustion will be X plus Y over 4. If Y is the only one having over 4, then what you have here will be X, and what you have here will be Y over 2. An example, let's assume 6 is H14 bonds in oxygen to give CO2 plus H2O. How many of these do you have? Just come here. Our X is 6, our Y is 14. So to get the number of oxygen atom, that will be needed will be Y divided by 4. Or let me use 12 to make it very simple. You can use 14 as well. You still get an answer. Or let's use 14, because some of you say you have changed it because it's going to be hard. So let's use 14. So 14 divided by 4 So x plus y over 4 gives you 6 plus 14 over 4. That is 6 plus 7 over 2. Isn't that? That is 6 times 2, 12. 12 plus 7, 19. That is 19 over 2. So 19 over 2. Then what would be here? X, that would be 6 would be here. Then what would be here? Y over 2, that is 14 divided by 2. 7. Are we there? So is it balanced? For you to know if it is balanced, just multiply through by, since you're having a fraction, multiply through by 2. So when you multiply through by 2 or with 2, you have 2 times the one that is here. 6 is H14 plus 2 times 19 over 2. That will give you 19 O2. 2 times 6, 12 CO2. 2 times 7, 14 H2. So let's calculate. How many carbon do you have? 12 carbon. How many hydrogen do you have? 28. That's 2 times 14. And that's 14 times 2. How many oxygen do you have? 2 times 19. That's 38. 12 times 2, 24. 24 plus 14. That's 38. So that's to show you. So it works for, so far it is an hydrocarbon, it works. Another property we'll be looking at is that they have low melting and boiling point. So hydrocarbons have low melting and boiling point generally, and this is the reason. Majority or all organic compounds, they have, the force that exists in them is the van der Waals force of attraction. The van der Waals force of attraction, we call it the London dispersion forces. London dispersion forces, LDF. That's the force that exists between them. And in the order of things, hydrogen bond, is greater than dipole bond, and dipole bond is greater than van der Waals forces. Let me call it the LD force. So, since what exists between them is London dispersion force, that is the van der Waals force, they don't really have strong bonding. No, they don't really have strong force of attraction between them. Do you understand? So it is easier to, for them to boil, for them to escape. When you eat them, it's easier for them to lose attraction and they escape. So they have low melting and boiling point. It is only those amongst them that have hydrogen bond. For instance, let's take the like of ethanol. Ethanol has hydrogen bond in it. Let's take hexanol. Hexanol does not have hydrogen bond. So what is only in it is London dispersion force. But this one has hydrogen bond. And don't forget that all organic compounds, they have London dispersion force. So it has hydrogen bond, it has London dispersion force. So its boiling point is greater than hexanol, even though hexanol is bigger than it. Hexanol is 6 carbon atom. Itself is just 2 carbon atom, ethanol. But it still has higher boiling point than hexanol. I think this should be 78 degrees for ethanol, and hexanol should be around 68 or thereabout degrees Celsius. So ethanol, they have low boiling and melting points. Now here is the point I want to put out there. I want you to note that. So we've spoken about their low boiling point and high boiling point. Now let's look at how their boiling point and how their melting point, how it either increases or decreases as big as they as they increase. So let's look at ethane, for instance. Ethane has 2 carbon atoms and 6 hydrogen atoms. Let's look at butane. Butane has 4 carbon atoms and 10 hydrogen atoms. Which of these two would have the higher melting point? Butane will have the higher melting point. Why would butane have the higher melting point? You see, their melting point or boiling point depend on the force between them, and the force between them increases as their carbon atom increases. The English I'm saying is this. This has 2 carbon atoms. This has 4 carbon atoms. The forces between these ones are much more than this one. Why are the forces between them much? Because the force of attraction depends on the number of electrons and the surface area. If you have to draw this one is just 2 carbon atoms. Look at the area compared to this one. You see, this one has a larger surface area than this. So the surface area contributes to the force between them. So if you have high surface area, you have high force, then you need high melting or boiling point to dissolve it. And the electrons too, they share. Look at, definitely this atom would have plenty of electrons than this one. So because the electrons in them increases with the number of carbon atoms, because their surface area also increases the number of carbon atoms, so their boiling point and melting point increases as well. So if I give you C6H12, H14, you should know which one will have the higher melting point and boiling point. This one's boiling point and melting point will be greater than this one, and this one will be greater than this one. Why? Because the carbon atoms it has larger surface area, it has more electrons than this. Now the last point I want to raise is this. So let's put the order this way. Okay. We will not put it in order first. Let me mention this last point. Then we'll now, we'll put everything into order. Let's look at 2-methyl. Forget the name for now. Just focus on, the message I'm trying to pass. Let's look at 2-methyl propane. This is 2-methyl propane. 2-methyl propane and butane, they have the same thing. C4H10. C4H10. Just that 2-methyl propane is arranged in a different way. We call that isomerism. When we get there, we'll talk about it. So they have the same number of. So if I ask you that which of these two would have the higher melting and boiling point, you should ask me that which one would have the higher force. So which one would have the higher force? Higher force depends on the number of electrons. You will have the same number of electrons now, isn't that? On the surface level, they would have. Don't let us go deep into the number of electrons because they have the same number of atoms. But would they have the same area? Let's look at. This is the area. For methyl propane, this is how it looks. But for butane, this is how it looks. Now, which one has the larger surface area? This one, of course, because it will be lengthier. It is longer. Let's use that as surface area. While this one is compact, it is packed together. So this one has larger surface area, meaning that because it has larger surface area, it has more forces than this one. So its boiling point and melting point, the boiling point and the melting point, or the temperature you will need will be to break it will be much more than this one because the forces are stronger. Now let's arrange every of them together. So let's assume you have we have propanol, then we have butanol instead. So we have butanol, we have butane, we have hexane, and we have 2-methyl pentane. So this is C4H5OH. So C4H9OH. This is C4H10. This is C6H14, and this is C5. Yes, this is H14. Just this one and this one, they are same. Just that the way this will be arranged, it will be like this one. So 5 long chain is what would you have on a straight line. Then these 2-methyl will just come under the second carbon atom. Now tell me, for a minute, I want you to think. Which do you think will have the, highest melting and boiling point, and why? Yeah, arrange it. Pause the video and arrange it. Pause the video and arrange it. So let's take the answer now. So I want to believe you've written something down. Now, which would have? Let's look at it in order of smallest. Butanol, butane. You look at this one is just 4 carbon atom. Should be the one that will have the smallest. Abi, we said the larger they are, the higher their boiling point. So which one is the largest? Hexane. So we are thinking hexane will beat this one, although they have the same number of carbon atoms. But then this one is compact. You understand? It means it will be like 5C, pentane, 1C on that. So that is why it is 6. You understand? So it is compact, unlike hexane that will be straightforward 6. So it has larger surface area. The larger the surface area, the higher the molecular force and the higher the boiling point of it. So hexane seniors in terms of melting point and boiling point, or let's say boiling point. Yeah, melting point sometimes doesn't go straight. So hexane seniors 2-methyl pentane, right? Because of area. Seniors butane. Why? Because of this one has lower number of carbon atoms than this. Then where would we fix butanol? This one is 4,4. So is butanol supposed to be here before butane? Because it has OH. No. Butanol seniors every one of them. Do you know why? It brings us back to this hydrogen bond. I told you hydrogen bond is stronger, than dipole bond. So for the fact that but is just 4, it's just 2 carbon atoms they used to senior. So butanol should beat them. Or let me change this to pentanol so that there will not be competition at all. So pentanol. So pentanol should senior every one of them. Or let's say hexanol. And this should be maybe pentane. I'm trying to make them a bit closer to themselves. C5, H11. So hexane seniors pentane, 2-methyl pentane. Hexane seniors 2-methyl pentane in terms of surface area. 2-methyl pentane seniors pentane because it still has extra carbon atom than pentane. This one seniors all of them because the hydrogen bond in it, seniors the London dispersion force, which is just a weak force. Now, the last property we are going to take, don't forget we've taken 3 covalently bonded. They are combustible, they have low melting and boiling point. And I told you how the boiling point, depends on surface area and number of atoms. It increases. They have low melting and boiling point, but it increases as the number of carbon atoms they have increased. And also straight ones, they have higher melting point and boiling point than branched ones, provided they have the same number of carbon atoms. I think you get that English. Straight one has a higher melting and boiling point than branched one, given the same number of carbon atoms. Now, the fourth property we'll be looking at is their solubility. They are generally, they are insoluble in water. When I use the word generally, or anytime I use the keynote generally, know that a vast majority of them, or a majority of them, cannot do that thing or can do that thing. It does not mean all of them. So generally, they are insoluble in water. They are insoluble in water. They are soluble in, if something is not soluble in polar, many times they will be soluble in non-polar. So if they are insoluble in water, it means they are soluble in non-polar solvents. So they are insoluble in water majority of the time. Now, there are some exceptions that are not soluble in water, that are soluble in water. Now, those ones that are soluble in water are those that have hydrogen bonding in them. Those that have hydrogen, for instance, OH, we call them the alcohols or alkanols. When we get to naming, you know what's the difference between alcohol and alkanol and why it's like that. So, alcohol, alkanol, OH. We have the COH, the alkanoic acids. Any compound you see having this, not any, many compounds you see having this, they are usually soluble. They are usually soluble. Why? Because they have hydrogen bond in them. Hydrogen bond increases the solubility of a compound in water. Once you have hydrogen bond, you have a tendency to be soluble in water. But there are other factors that might not make you soluble in water. There are other factors that might not make you soluble in water. So as I said once you have hydrogen bond, you have tendency to be soluble in water. But there are things that can prevent you as well. This is the reason. You see hydrogen bond in these two, they are soluble. But the carbon bond is insoluble. So if in a compound, the carbon bond in it, this carbonyl bond in it is more than the hydrogen bond in it, that compound will be insoluble. But if the hydrogen bond, has the higher power, it will be soluble. But once you see OH compound, they are usually, soluble. This is what I'm saying. Look at ethanol, for instance, C2H5OH. It is soluble because the hydrogen bond and the carbon bond is like having almost the same power. The hydrogen bond, power exceeds or supersedes the carbon bond power. If you go to, as it increases, this one too is miscible. Still soluble in water, or let's say slightly soluble, or let's just use the word soluble for it. If you go down, C4H9, you can see the carbon number is increasing, and it is increasing, it is reducing the solubility. So this one we can say is miscible. Mainly you start getting to C5H12OH or C6H13OH. This one will be slightly, because you're already overpowering it. Do you understand? So the same thing to COH. If you have C3H7COH, you're already overpowering the hydrogen bond in this. So this might be slightly soluble. Are we good to go? So, but hydrogen alcohols and alkanoic acids, they are usually soluble because of the hydrogen bond present in them. Now, another thing you can do is, let's imagine you have C2H5O, CH2OH. Now look at this case. You can see you have double hydrogen bond. You have, the hydrogen bond, this will be much because the OH you're having now is 2 times. So this 2 will be very soluble. You will understand? Be very soluble. So if you have plenty COH bond too, it will be soluble. To test your understanding as well, let's consider these 3. Propane 1, 2, 3 triol. Propane 1. Don't worry, you know how to name all these. Once we get to naming, this is the formula: CH2OH, CH2OH, CH2OH. Look at propane 1, 2, 3 triol. Look at pentanol, that is C5H11OH, and pentanol and propanol, that is C3H7. So let's arrange them in order of increasing. Which one will be the most soluble? You can can see that we say the more the number of carbon bond, the lesser the solubility. Which one has the highest carbon bond? This pentanol. So it means pentanol will be the lowest in terms of solubility. So pentanol is less than which one again? So propanol, because it does not have too many carbon atoms. Propanol. Although propanol and this one has the same number of carbon atoms. This one has a lot of hydroxyl bond, which makes it have a lot of hydrogen bond, and hydrogen bond supports solubility. So it's less than C3H6. C3H. Whatever we want to write it. 2, 4, 6, 8. It means this is the most soluble, followed by this one. This one rather. So this is the most soluble, followed by this one, followed by this one. Or we should write it this way, that CH3 is greater than this. It's greater than call it glycerol. We will go into the classification of organic compounds. Classification of organic compounds. So, still tailored to the curriculum of the school, we will be taking classification the way it was classified as well. So, number 1, it is classified based on the structure. Based on the structure. Structure means how they appear, how they are seen. You know, it's their skeleton. So how are they seen? So we have 2 classifications under that. The first classification, we have 2 divisions under that. So the first division we have the acyclic. So acyclic means, you know, those compounds you see, the organic compounds you see that they have, you know, they are open. That's the word I can use. That they are open. They are called open chain. Examples you have is straight chain, straight chains, and the branch chains. You have the likes of alkane. When you see them, they are not closed. They are just plain. They are open. So the likes of these straight chains, having hydrogen, like propane, alkanes, alkenes, alkynes, they are straight. They could be branched as well. They could be branched as well. They are still open. They are still open. They are open. You understand? So they are open. You can move to every part here. It's open. Something you are seeing. It is not closed. It is not forming a closed shape. You understand? This will lead us to the second division under the structure, and that is the cyclic, or the closed chain. It's like cyclic or the closed chain. Under this cyclic or the closed chain, you have 2 divisions as well. You have the alicyclic. These alicyclics, they are all non-aromatic. They are non-aromatic. This one, they form a closed shape, but they are non-aromatic. When we get aromatic compounds, all those Swiss-Menu compounds, we get to know more about them. So for now, we just want to talk about, their classification based on structure. So the alicyclic examples, you have the cycloalkanes, e.g. the cycloalkanes. Let me quickly, buttress some points on that cycloalkanes. The cycloalkanes, they are alkanes. They have single bond up through in their chain, but they have the formula of the alkanes. Alkanes are known to be CnH2n plus 2. These are alkanes. That is, the straight chain and the branch chain, they are cyclic. Alkanes belong to their cyclic because they are open. You can see them, they are not forming a closed chain. But these cycloalkanes, they are alkane in the sense that they have a single bond, but their formula is that of alkene. You understand? CnH2n, meaning you remove 2 hydrogens, this plus 2 hydrogens from alkanes to get cycloalkane, and by so doing, what you are having is alkene in terms of the formula, because alkene is CnH2n. So cycloalkanes are like sharing 2 things. They are having the formula of alkene, but they are having single bond as alkanes. You understand? So they belong to this category because when you draw them, for the carbon to retain 4 bonds, let's look at cyclopropane. Now propane is 3. it's supposed to be C3H8 propane. But if you remove 2 hydrogen from it, it becomes C3H6. So how will carbon still retain 4 bonds? You know, carbon is tetravalent. It has 4 valence electrons. So look at this first carbon has 1, 2. Do you understand? So how does it become 4? It has to be in this circular shape, in this closed shape rather. Now look at 1, 2, 3, 4, 5, 6. And each carbon is having 4 electrons. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Do you understand? So cycloalkanes, they just take the shape of polygons. You know, if you're talking about cyclobutane, that's 4 but. So what shape has 4 sides? That is a rectangle, a square. So just draw a square. Draw a square, a circle at the edge, then 2 hydrogens, 2 hydrogens. So this way you get C4H8. And your carbon, that's 4 bonds. So this is cyclobutane. Why this is cyclopropane? So these are cyclos. You understand? They belong to the alicyclic. So the second division under cyclic, we have the aromatic compounds. These ones, they are the benzene and its derivative. Compound. So this ones, they form closed. Look at this now. Is it not closed? Closed chain. That's why I call them cyclic. A circle. Yes, a closed chain. Look at here. You can have something without going out. You can pour water here. You can the water from it. That's just by the way. So aromatic too. We have likes of benzene. So this is benzene, or it could be in the ring form. Alternatively, that's what we call resonance. It could be in another form now where the bonds are alternating. So these ones, they are also close, but you can see they are double bonds. Unlike the cycloalkanes, they are not double bonds in them. If I want to draw cyclohexane, that is single bond, but it is a closed shape. You know, cyclohexane, I said they are polygons. Hexane, that's 6 sides. That's just draw an hexagon. This should be cyclohexane. So this is cyclohexane. No double bond in it. Cyclohexane. It does not belong to this aromatic. It's here. It belongs to this alicyclic. I'm trying to show you the difference between cyclohexane and benzene. So you see that no double bond in any of this, because no double bond, and it will be C, and it will still be 4. 1, 2, 3, 4. You get it? 1, 2, 3, 4. Do you understand? Yeah. But in the case of this one, how would the carbon be 4 bond? It is already 1, 2, 3. So you just need 1 hydrogen to be complete. You understand? So 1 hydrogen, just 1 hydrogen in every of the cases. That makes it C6H6 for benzene. Do you understand? So now let me rub this off. So this is cyclohexane. It's not supposed to be here, it's supposed to be here. So in aromatic, you have the likes of benzene, you have the likes of phenol, you have the likes of toluene. All these are derivatives of benzene. They are benzene, then you add something to it. For instance, you should have benzene, then OH. Then let's say you have OH, the likes of phenol, benzene, then you have CH3, that is methyl benzene. Likes of toluene, aniline, benzene, then you have ammonia, NH2. You understand? So they belong to the aromatic. Now the second classification that we'll be looking at is classification based on functional group. For now, before we talk about functional group, before we add points to it, just take functional group as based on profession. The profession, that is the work you are doing. Just take it, okay, functional group, you are like, okay, this is a teacher, this is a doctor, or a characteristic, just a property that can tell something about it. So just take it that way. So based on functional group, we can classify them based on functional group. There are those we see as purely they are hydrocarbons. That is only containing only hydrogen and carbon. Examples, you have the likes of alkanes, alkynes, like that. They just have carbon, hydrogen. You understand? We have those we can classify as oxygen containing. They have oxygen in them. Yes, the likes you have the alkanal, CHO, alkanol, ROH. Do you understand? You have the likes of alkanoic acid. So these ones, they have oxygen in them. So you'll be seeing things like so these are just Roman figures in case you're not clearly seeing. So alkanol, you have the CH3OH, like methanol. You can see it is having oxygen in it. Alkanoic acid, ethanoic acid, it's having O in it. So those are the oxygen containing. Another one, you have the nitrogen containing. The nitrogen containing. You have the likes of amides, e.g. the amides. You have the amine. Amines. So when you have CH3, CONH2, like the ethanamide, methanonitrile, and so on, methylamine rather. So what else? You have the halogen containing. That's what you have, chlorine, bromine, with an organic compound. So those are the halogen containing. So we have different classification, different divisions under this classification as well. So that marks the classification of organic compounds.